Welcome back! In this lesson, we'll discuss one of the most important practices for our landscape, constructed wetlands. And just a reminder, I hope that you'll be thinking about how all of these practices work and their benefits and challenges for implementation.
There are many different kinds of wetlands. For example, coastal wetlands, riverine wetlands, wetlands associated with lakes, and there's also natural wetlands, restored wetlands, and constructed wetlands. Each of these different kinds of wetlands is unique with different nuances. In general, wetlands are dynamic ecosystems of plants, soil, bacteria, and water. Today we're talking about constructed wetlands or treatment wetlands that are specifically designed and constructed to treat nitrate in subsurface drainage water. Within the classification of treatment wetlands, there are surface flow or free water surface wetlands, which have an open water surface, and subsurface flow wetlands, which use generally gravel that water flows through. Here's a couple illustrations of the different kinds of constructed or treatment wetlands. Surface flow wetland on the left and subsurface flow wetland on the right. The mode of action, or the mechanism for how wetlands clean nitrate from water, is primarily via the process of denitrification. There's also a little bit of plant uptake of the nitrogen and the water, and a little infiltration of the water out of the wetland, which reduces flow volume. But in general, with wetlands, we're talking about a nitrate concentration reduction in the wetland due to the process of denitrification. And you'll remember that concentration and flow volume give us load. So we're looking for a concentration reduction, primarily leading to our load reduction of nitrogen with a wetland. As a recap on denitrification, this is the microbially mediated reduction of nitrate either in soil or water, or in our case today a wetland, reduction of nitrate to dinitrogen gas. Intuitively, because denitrification is a biological process, the amount of time nitrate spends in a wetland influences how much nitrate is removed. That makes sense because the denitrifiers need enough time to do their process of this nitrate reduction. Hydraulic retention time is defined as the porosity of the media times the saturated volume of the wetland divided by the flow rate. For a subsurface flow wetland, we're generally looking at depths of 1 or 2 feet, and then to get your saturated volume, you would multiply that by the surface area. Depths of 1 or 2 feet for a subsurface flow wetland, and then the porosity of the gravel of generally 0.3 to 0.5. That is 30 to 50% porosity. For a surface flow wetland, where there's open water surface, you're looking generally at a depth of 0.5 foot to 1.5 foot. And then of course your porosity is 1 because there's no media that you're flowing through. It's essentially one big pore space. So that's 100% porosity. These depths are an important concept for you to lock in regarding wetlands. And when I was learning about wetlands, I was very surprised about this. Wetlands are specifically defined as being shallow. So here we're talking no more than 2 feet of depth of water. We're not talking 3 or 4 feet, less than 2 feet. It's a very shallow, wetlands are a very shallow water body, and that's what allows the wetland plants to be a part of the system. So wetlands are specifically defined as being shallow. Let's do an example with this hydraulic retention time. Say we have a 3-acre surface flow wetland that is 1 foot deep, and we know the flow rate is 150 gallons per minute. So let's calculate hydraulic retention time. HRT is a common abbreviation there, equals the porosity. Well, this is a surface flow wetland, so I'm not flowing through any gravel, so my porosity is basically 1 times my saturated volume. I know I have 3 acres. Let's convert that. 1 acre is 43,560 feet squared. So 3-acre wetland surface area is actually 130,680 square feet. So 130,680 feet squared times, and I'm going to add some parentheses here, times my depth is 1 foot, so that's an easy one, times 1 foot divided by my flow rate. So I'm going to do 150 gallons per minute, and I know there's 7.48 gallons, got to get my conversion right, in a cubic foot. 7.48 gallons in a cubic foot, so I know my 150 gallons per minute is actually 20 cubic foot, 20.1 cubic foot per minute. So then on the bottom, I'm going to put that over 1, just so I can divide my equation out, have my units straight. I'm going to do 20 cubic feet divided by minutes on top, because I'm looking for a time. So my units here at the end should be a unit of time, because this is hydraulic retention time. When I work that math through, I get 6,517 minutes, which equals 4.5 days. So my hydraulic retention time is 4.5 days. Wetland effectiveness is essentially a function of hydraulic retention time, and hydraulic retention time is a function of the size of the wetland and the flow rate that comes in. The flow rate that comes in is related to the drainage area. You can see from this graph during high flow events where those blue lines peak, where you get real spiky periods for the flow rate, which is shown in blue, there's a decrease in nitrate removal. Or in other words, where that blue line peaks, the red dots and the green dots converge, because the wetland doesn't work as well when you're trying to force a lot of water through too quickly, when the hydraulic retention time is very short. Recommended wetland surface area needs to be, for constructed wetlands in a tile drainage landscape, needs to be about 0.5% to 5% of the watershed or drainage shed, and then you have to have an associated buffer around that wetland that's generally about 3.5 times the wetland surface area. For example, if you have a 100-acre watershed, you would need about a 1/2 acre wetland up to about a 5-acre wetland, and then at least a couple acres of buffer around that wetland. Generally, you're looking at 1 to 2 acre wetland for a 100-acre watershed. Wetlands are an extremely effective practice for nitrogen loss reduction. They're one of our most effective, consistent practices for nitrogen loss reduction, and you see that consistency reflected in the values from the Iowa, Minnesota, and Illinois nutrient strategies here in this table. Phosphorus loss, however, is a little trickier. You'll also see very consistently across the strategies, no phosphorus loss reduction credit is assigned for wetlands, and that is because of the full bathtub concept.
You turn the tap on, the bathtub fills, and with the tap continually on, the tub will eventually overflow. In a wetland, phosphorus comes in and nitrogen comes in, but remember the nitrogen gets denitrified, whereas there is no gas phase for phosphorus. So any phosphorus that comes into the wetland stays in the wetland. Dissolved phosphorus can be taken up by aquatic plants for plant growth, but unless those plants are harvested, which they're commonly not for wetlands, the phosphorus will stay there in the plant material and become cycled into organic matter in the wetland. All this means is that the ultimate fate of phosphorus entering a wetland is that it stays inside the wetland, and the full bathtub concept is that after a period of time, any phosphorus entering will equal the amount of phosphorus leaving.
Last note on this, it may be that wetlands should get an initial phosphorus loss reduction credit when the wetland is new, before that wetland has really saturated with phosphorus. Some wetlands advocates are promoting this idea, but we haven't actually added that into our state strategy yet. Some significant limitations or barriers for getting constructed wetlands back into our landscape. Primarily, there's concerns about taking land out of production. Like we discussed a minute ago, this does require a relatively significant amount of land depending on the amount of drainage area that you're trying to treat. And this is just really one of the biggest barriers. There's also a pretty sizable construction cost, upfront construction cost. And then I also want to say there's some, I think, more subtle historic and cultural barriers, and really policy barriers that we deal with. One being, we've been draining the land in our landscape for over 150 years. And so to think about intersecting those tiles, plugging those tile pipes, and getting wetlands back into our landscape really requires a 180-degree shift in our thinking culturally in this part of the world. Wetlands also tend to be a relatively regulated water body based on the Clean Water Act, and many landowners don't want to touch that with a 100-foot pole. The state of Iowa, though, has had particular success with a very large wetland program where they aim to treat drainage from at least 500 acres. So we're talking about drainage areas of 1,000, 1,500, 2,000 acres. These are not field scale wetlands, but rather more drainage district scale wetlands. This is an attempt to really scale the practice of wetlands and efficiently target wetland placement to provide the maximum benefit. And this is, like I said, one of the most effective wetland programs I know of because the financial incentives are right. And the practice is scaled to provide a large benefit. For example, incentives include annual rental payments that are actually more than what the regular rental payment would be, 100% cost share for the wetland establishment or restoration, and then a one-time upfront incentive to enter into a long-term easement. And so the financial incentives are really there to compensate farmers for putting wetlands back in the landscape.
This is the end of the slides, but if you're interested to hear more and see some examples of great wetlands in Illinois, I suggest the supplemental video.